We're going to continue on the next part of section 13.2. This is going to focus on the position, velocity, and acceleration time functions while something is in SHM. So let's start with the position time function of an object in oscillating in simple harmonic motion. All right. So the most basic position time function takes this form in this box right here. The position x is equal to a amplitude times the cosine of the quantity omega t plus phi, where phi is defined as something called the phase angle, which we'll mention more later. So what this ends up being, if you remember your basic trig, is a basic cosine function. Just looks like a sinusoidal wave pattern that starts out at t equals 0 on the crest of a wave. That's a high point. Now, while that's true, that will only start that way as long as the phase angle phi equals 0. If the phase angle is not 0, it may start at different positions of the wave at t equals 0, shifted depending on how many radians or degrees that phase angle is set at. But let's not think about too much of that for now. If phi is 0, then this will look something like this. The amplitude A, whatever value comes in front of the cosine, is the maximum position away from what we call the equilibrium position. So let's say this is a spring pendulum bouncing up and down. So whatever actual value is here is the maximum positive amplitude, and there's always a maximum negative amplitude. Think of the t-axis as the equilibrium position because it's smack in the middle of positive A and negative A. And the omega, what that changes about the graph would be basically how horizontally compacted it is. The omega, the angular frequency, is basically based on the regular frequency and time period. Remember how all those three are kind of tied together in some of the equations from earlier in the section? That allows us to see, like, maybe if it's bouncing up and down faster, that these crests and troughs of this wave pattern are more tightly packed together. And don't forget, big T would be the time it takes for one full cycle. One full cycle is, for example, from positive A down to negative A, back to positive A. The time it would take this object to go through this portion of the graph from here to here would be time period T. That's just one example. You could use any two repeating points, but crest to crest, high point to high point, or trough to trough, low point to low point are the most distinguishable. Now going on to the velocity time function, which if we would take the first derivative of the position function, that's how this is calculated, of the position time function. So using your basic trig derivatives and knowledge that you should have from calculus, if we take the first derivative of this function, it would yield the velocity time function, which looks like this. Negative omega a sine of the quantity omega t plus phi. There's that phase angle again. Now this is a sine function. If the phase angle was 0, then it would look like a typical sine function starting at the equilibrium position at t equals 0. Going on and continuing that pattern, if we took the derivative of the v of t function, that would give us the acceleration time function. Or you could think of it as taking the second derivative of the position time function, and that would yield the equation right here. So we should all be capable of the calculus to get from one of those to the next. Now after this, I'm going to save some time here and not show you all the derivation, but with some substitution going on with some of these equations and some of the other ones above in the chapter, the smaller equations, we could find some other formulas for acceleration. Some of them being that the acceleration of the object in SAM being equal to negative omega squared times its position at any given moment x, or that is also equal to negative k, the spring constant k, over m times any position at any time t, which is defined as x. Some other ones with finding a phase angle, especially if it's non-zero, phase angle equals the arctangent, or in other words, inverse tangent, of the quantity negative initial velocity divided by omega times the initial position. And finally, another helpful one for amplitude, if we don't know it, would be kind of this ugly formula. You could read that to yourselves there. But those are all important formulas for knowing features as described above. So with all that in mind, let's look at example 13.3 to finish off this section. So I'm going to flip to the textbook. This is on page 428 of the PDF version of your textbooks. All right, so it says, let's return to the system of mass and horizontal spring we considered in example 13.2. So that's the last example we did earlier in the section on the prior video. The spring constant K is still 200 newtons per meter. The mass is still 0.5 kilograms. This time we give the body an initial displacement of positive 0.015 meters. So that's actually the initial amplitude, because where we release it from, and an initial velocity of, actually, let me change that. That is not the amplitude 0.015. It's just an initial displacement for right now, x sub 0, basically, the position at t equals 0. So let's make sure we realize that 0.015. And an initial velocity, v sub 0, of 0.4 meters per second. First, we want to find the period, the amplitude, and phase angle of the motion. And then B, write the equations for displacement, velocity, and acceleration as functions of time. So we'll apply a little bit of everything we did before. So at this time, I'm going to flip over to the notes where I solved for this. Excuse me. And let's solve for part A. All right. The period of this oscillator from the prior problem would also be the same. We can make that connection. So if the period is still the same, that would mean omega is still the same, 20 radians per second, as in problem 13.2. So to find the amplitude, we use one of the formulas defined above and just pop in the numbers. The initial position 0.015, the initial velocity 0.4, and the omega 20 all goes into the amplitude formula, and that would mean this has an amplitude of 0.025 meters. And technically that amplitude could be positive or negative due to the fact there's always a high position and low position of amplitude compared to equilibrium. Once knowing that, we can now move on to finding the phase angle using the phase angle formula and those values from above and popping them in. Phase angle ends up being negative 53 degrees, or if you convert that to radians, negative 0.93 radians. Now that we know all those values, it'll be pretty easy to write all the formulas. If you recall, a position time graph or position time function was x equals a times the cosine of omega t plus or minus the phase angle, and the phase angle came out negative, so we can see a minus is there. All we got to do is plug in those numbers. So amplitude is 0.025, it goes there. Omega is 20 and minus 0.93. We typically write this in radians and not degrees here when writing these functions. Then using the velocity time function above, we're going to plug in those same numbers, and if there's any small calculations, we'll put them together. So there's an omega here, amplitude there, multiply those, you get 0.5, plug in everything else, and do a similar thing for the acceleration time function. And you could see us plugging those same values in and condensing anything down to possible. So there's our three core functions dealing with position time, velocity time, and acceleration time of an object like this in simple harmonic motion. As always, I hope these help, and after doing some of the problems based on it, please contact me any way possible if you guys have questions.